Good day, everybody. This is Christopher Bear, and this is going to be video 2 for Module 1, Assignment 1 in Biotransformation and Molecular Mechanisms of Toxicity, University of Florida. This will be spring 2015. All right, so in the first video, we talked about cytochrome P450 oxidase, and we talked about the general reaction. But at the beginning, we had discussed this particular molecule here, and I actually have a molymod setup of this, a stick and ball setup of this molecule. And this is a molecule of 4-chlorotoluene. So what do I have? Well, I have an aromatic ring, I have a methyl group here, and I have a chlorine atom here. And so we said that this particular molecule, following a reaction, a phase 1 biotransformation reaction mediated by a cytochrome P450 oxidase enzyme, there were two distinct metabolites that happened to be structural or constitutional isomers of one another. These were hydroxylated metabolites, and there was one metabolite. Look like this. I'll throw a hydroxyl group on there. All right, fair enough. Okay, so you had a substitution of the hydrogen. This hydrogen was substituted with a hydroxyl group, and then the other substitution, or the other isomer, if you will, actually involved having the chlorine down here and the hydroxyl group up here, like so. So I have these isomers where the chlorine and the hydrogen atom kind of swap places, and the question is, what's going on there? What's happening? What's causing that? So first of all, what we need to understand is the general mechanism or the general reaction that occurs is something known as epoxidation. And when I have an epoxidation reaction, basically what happens is an intermediate step is I take a double bond and I turn this double bond into a single bond. So here you can see that I have my resonance structure, and one way of looking at a resonance structure is alternating double and single bonds. Of course, we know in reality the electrons are rather delocalized, but one way we can look at this is alternating double and single bonds. And so what can happen is during the process of this reaction, okay, the bond, the double bond next to the chlorine here, all right, move that toward you guys here. Okay, I can have epoxidation of this, and I actually have an example of an epoxide or an oxirane. This is just a very, very simple molecule, very basic example. This is ethylene oxide, and you can see at one point that this was probably, or this was at one point, an alkene, had a double covalent bond. The double covalent bond is broken, and each carbon has a single covalent bond to a oxygen here. So what happens is during that process, okay, the reaction we talked about earlier, this double bond undergoes epoxidation, Na oxirane, or because we're dealing with an aromatic ring, an arene oxide is produced. It's the same thing. Epoxides, arene oxides, oxirane products, they all mean the same thing, but an arene oxide would be probably the most accurate description because it actually acknowledges the presence of an aromatic ring. So this is converted into this here. Okay, so if you can imagine that I have oxygenated this, okay, I have a monooxygenation that has occurred. This double bond here is broke, and I have this single bond here, and that's how the oxygen gets added. However, this tends to be a very unstable configuration, high energy level, and the molecule, this intermediate, okay, this intermediate oxirane product or arene oxide product will quickly transition back to its aromatic structure, and when it transitions back to that, the double bond is formed, but I have this hydrogen here replaced with a hydroxyl group, and then I have my new metabolite that's formed. However, one thing to note is whenever you halogenate one of these carbons and you have epoxidation occurring, okay, and you have a halogen such as chlorine, you get chlorine, bromine, fluorine, I suppose. Although that'd be really electronegative and highly reactive. All the halogens are very electronegative. But if I have a halogen here, as you can see right here, I have my halogen. If I have a halogen next to the double bond that is undergoing epoxidation, something rather interesting can happen. This sets up a situation where there is a sort of extra reactivity, and that actually allows migration of either the chlorine or the hydrogen here. And so what can happen is, as this oxirane product reestablishes, okay, turns back into the aromatic structure, I can get a migration of this hydrogen or this chlorine, and occasionally the chlorine can migrate back over here, all right, and I have a hydroxyl group that gets, the hydroxyl group gets attached there, or the chlorine doesn't necessarily migrate, all right. I have migration of my hydrogen, and I end up having the hydroxyl group attached here off of this carbon here. Either way, you can have intermolecular migration of the chlorine or the hydrogen atom, and they can kind of swap over. And that shifting is known as an NIH shift, and the NIH shift is the mechanism that can actually results in the different isomers of the metabolites. The NIH shift is actually named after the National Institutes of Health, and that was where that particular mechanism was first described. So hopefully this video helped and gave you kind of a visual representation of the exact reactions, the epoxidation of the aromatic ring when you have monooxygenation of this particular type of structure. Okay, hopefully you found that helpful, and as always, thanks for hanging.